All right, welcome to your fourth web lesson. Today we're going to be talking about proving congruence like we did in the last lesson, but we're going to look at some different techniques for doing that. Yeah? So let's jump in. Last lesson we said that in order to prove that two triangles are congruent, that is that all of their parts are also congruent, we don't actually have to prove that the three sides and the three angles are congruent. We can take little shortcuts, because by proving things like the fact that the sides are congruent, that will necessarily mean that the angles are also congruent. There's no way out of it. And so, like we said, if we can do this, we also know this. Okay? Now, SSS is not actually the only way of proving that two triangles are congruent. There are other ways as well, and this has to do with, like we said, the fact that triangles are a super interesting figure when it comes to geometry, because you change one part and all the other parts change. Well, not necessarily all, but other parts in the triangle change along with it. And it's impossible to change one thing without changing the other. There are these interesting relationships that are always shifting within the triangle as you change different parts. Oh, I forgot to do this here. There you go. So let's look at other ways. Okay, so I've written at the top of the board here the 4 ways that we're going to look at proving that two triangles are congruent. And we've already looked at SSS, so that's pretty simple. We'll cross that one out. Now here we have SSS. Can you take a guess at what that might mean? It's pretty obvious. It means side, angle, side. Okay. So all it simply means is that if we have two triangles, I'm going to do them without any transformations so that it's less confusing. We can prove that the entire triangle is congruent to this entire triangle by simply proving that one side is congruent to another side, one angle is congruent to another angle, and another side is congruent to the other side. Now, one thing that's interesting about this is that it can't just be any side. Notice the order: side, angle, side. The angle is actually sandwiched between the two sides, right? And this is actually called an included angle. And that's what we're going to need in order to use this method of proving that two triangles are congruent. So, ABC, DEF, what this postulate says is that if I have this congruence, then in fact triangle ABC is congruent to triangle DEF. And we could go into proving it, and all of these postulates can also be proved, but let's just think about it a little bit. If I have an angle here, and let's say I didn't actually have this side. Say I didn't know the length of that side. Yeah? Now if I have a side here, and I have an angle and a side, and I have a side the same length and an angle and another side the same length, well, what is going to be true about this third side? Can I actually draw this side in any other way than this one? Can I make this side a bit longer? Well, no, that's not possible, because if I make that longer, I'm going to actually end up changing the measurement of the angle. So already I know that if I have this, I know that this third side is going to have to be congruent as well. And in fact, if you think about it a little bit, the fact that I know this angle and the length of this side, and I know that the length of this side has to be this exact length, that's actually going to determine exactly the measurement of this angle as well as this angle. But all I need is the SAS. So that's pretty cool. It's a quick way of proving triangles congruent when I don't actually know the length of the third side. All I need is this side, a side, and include an angle, and a second side. A side, and include an angle, and a second side. So let's take a quick look at a possible proof that uses this SAS method. Let's take a quick look here at my cheat sheet. Okay, so let's say I have a figure that looks something like this. That hourglass figure that we've seen before. Okay, so the given in this case is going to be that D, oh, my marker's running out, DE and BC bisect each other. And that's my only given. What I have to prove is that triangle DGB is congruent to triangle EGC. Okay, so let's take a look here. Let's take a look at my given. It says DE, here's DE, and BC, here's BC, bisect each other. Now, if you remember, what does it mean for two line segments to bisect each other? Well, it means, remember, bis from Latin means two, right? So it means to cut in two exactly. So I'm just going to actually do this quickly and put it on my diagram. I don't know that they're actually the same length, so I'm going to use different markers for that. But I do know that that has to be equal to that, and that has to be equal to that because of the given. So let's quickly write a formal proof. Statements, reasons. 1, DE and BC bisect each other. Oh, I have to copy it. DE and BC. I'm just going to put bisect. Okay, how do I know that? That's the given. Very easy. Now, how am I going to get from this to the fact that this entire triangle is congruent to this entire triangle? Well, one way would be SSS. And in order to do that, I would have to prove that this side is congruent to this side. But I don't really have a hope of doing that because it doesn't seem like I have any information that's going to tell me that this is congruent to this. But what I do have, if you look at the diagram, they're very sneaky, is a certain special type of pair of angles. Do you remember what those are called? Yeah, those are vertical angles. And we know that those are always congruent, right? Because that's just the nature of vertical angles. There's no other way. And so I'm just going to mark that on my diagram right away. So I'm going to put that right here, and I'm going to say that. Oof, my marker, come on. I'm going to say that angle BGD is congruent to angle BGD, angle C, oops, forgot the angle, angle CGE. And I know that that's true because these are vertical angles. So, in fact, I could have had an intermediate step that says angle BGD and angle CGE are vertical angles, and the reason would be diagram. I'm going to skip that step, and I'm just going to go ahead and just say that they're congruent, and I'll just put all vertical angles are congruent. Just a real quick way of writing that. Now you'll notice that, if you're quick, that I'm actually already done. I have a side, an included angle, and a side, and included angle, a side. So I know that in fact all the rest of the parts of these triangles, the corresponding parts, are going to be congruent too. based on this SAS postulate. So I'm just going to go ahead and write that. Triangle DGB is congruent to triangle EGC, and that is, I'm just going to put SAS, right? And SAS, like I said, is just a shortcut. I could go ahead and I could prove SAS if I wanted to, but it's been proven for me, and let's say that I trust the proof that the mathematicians before me did, and so I'm just going to put that as my reason and be done. Okay, so let me go ahead and erase that. Okay, so we're done with SAS. Now I'm not going to go ahead and give you an example of all of these other two methods, but we will explain really quickly how it is we can use them. Right? ASA, I'm sure you've guessed, means angle, side angle. And this means that I'm going to be able to prove that two triangles are congruent by just using an angle, if I can find that those are congruent, an included side, and another angle. Just like that. Again, the order is important. It's important that the side be an included side. So if I can prove these three things, then I can know that all the rest of the parts of the triangle are congruent. And in the same way, you can kind of see that the measurement of these angles are going to determine the measurement of the third angle, as well as the length of the sides. In fact, there's no way that I could draw those sides differently on this side if those angles are congruent to those. So that's just a quick explanation of angle, side angle. You can use that in proofs, and that's just one among the four that we're going to look at. So let's go ahead and cross that out. And the last one is going to be, I'm sure you guessed it, angle, angle side. Okay, and very simply, there we go. Okay, those are supposed to look the same. If I can prove that one angle is congruent to another, a second angle congruent to a second angle here, and a non-included side. You can tell that it's different from ASA, yeah, because the side AS is on the outside, so that's referring to the fact that this side is not included, meaning it's not sort of sandwiched between the other two angles. And that's going to be enough also for me to, for me to prove that these two triangles are completely congruent to one another. So in a proof, you could use any of these four as long as you can find out a way of showing that three sides are congruent, or a side, an angle, and a side are congruent, or an angle, a side, and an angle, or an angle, angle, side. So my laptop's running out of battery. I'm just going to plug it in really quickly. Sorry about that. So that's your lesson for today. Let me give you your assignment. As always, we're going to do check for understanding. And this is in lesson 5.4 of your book. And I want you to do you're going to do check for understanding number 5. And I'm going to actually split this into two, so I'm going to post both on the blog. And the other check for understanding is from 5.5. So this is from 4.5. And in 5, let's see if I can make it last. In 5.5, you're going to do number see here. You're going to do number 5 as a proof. And you are going to do let's see here. Number 8. That's all. Okay? So go ahead and you bring that into class and I'll give you some points for it and I'll see you in class. Bye-bye.